A computer will solve this way faster than a human can. How do I know? My wife was working on this problem. It was kind of hard. And I said, I bet I could code that up faster than you can solve it. And she said, you're on, go. So I started coding it up. She started solving the puzzle. Guess who won? My wife. She's blazing fast. But moments after she found the answer, I finally had my code working, and I hit go, and instantly it found the right answer. And then I asked her, was your solution optimal? Ha ha ha! I found the optimal solution moments after my wife found a solution. And yeah, she had moved pieces back and forth many, many times. So, for the extra little cost that it cost me, I not only found the optimal solution, I had a documented path from the beginning to the end of the optimal solution. So I claim victory even though she technically won. And that's the other thing, is now I have the code implemented so it generalizes to all kinds of problems. Could you solve a Rubik's Cube with this? Sure, just you have a starting state, somehow you encode your cube, and then go through all the possible combinations until you find a solved state. Rubik's Cube solver. Could you run a maze with this? Sure. Could you run a hyperdimensional maze? Sure. Could you, basically, in theory, assuming that you're the only actor in the universe, and you can encode the whole universe, and you have a Turing machine with arbitrary amount of memory and is sufficiently fast, this algorithm is general AI. Any problem there is, this solves it. Even if it's continuous space, we just discretize it to an arbitrary amount. Even if it's, if you think about it, AI is done. There you go, all problems are solved right there. Except for it does use up way more memory than most machines have for a lot of interesting problems. And except for there's a lot of reasons why this doesn't really work. And we're not usually alone in the universe. And for lots of reasons, this doesn't solve everything. But in theory, this is the only thing you need, and you get AI. And that's kind of cool. OK. What if we had searched in a depth-first manner instead of a breadth-first manner? Will that eventually find the goal? Yes, but here's the path it'll follow. Oh, dang, it found the goal really fast. Pretend those goals aren't there. Etc. until it comes around here and it's still coming along, and then it'll find the stupidest path imaginable until it winds around in and finally lands on a goal. There's a good reason we don't use depth-first search. If you took my programming class, we actually used depth-first search to make a little Mario run around. And that's great because the game was designed to be able to handle it. We used a few heuristics to make it work out. But breadth-first search works a lot better than depth-first search for finding optimal paths. OK. We were looking at the pseudocode for this. I want to make sure you get the pseudocode and know how to code it up. OK. Do you know how to make a queue in, say, Java? Sure. You can use an array list if you want. It's easy. OK. Do you know how to make a set in Java, or whatever language you're going to be coding this in? I think a set's not too hard of a thing to implement. There is a set class. I like to use tree set. Hash set can be faster, but you have to know how to use a hash set. I think I give an example of tree set in some of the help code down at the bottom of the instructions, so maybe look there if you are uncomfortable with sets. You can use their dictionary approach here, or you can just use a linked list in your states that link to the parents. This is dictionary. What they're doing is they're mapping from every state to its parent state. Do you see how that's a dictionary? The current state goes in, the parent state comes out. It's a mapping. Or you could put it in the state itself, however you want to implement that. So get the problem's root. What they're saying is, what's your start state? OK. Meta root none none. I don't even know what that is. I think they're saying, oh, this is the dictionary. They're saying the parent of none is none. I'm uncertain what that is.
That makes sense.
OK. In queue, the root. Do you see we're saying put the starting position into the queue? OK. I'll get to your question in just a second. I just want to finish going through the pseudocode. We have a loop here while the set is not empty. In other words, as long as there's a frontier still expanding, here's what we do. We pop something out of the queue. visit all of the child nodes from it. So we're going to loop through all the 44 possible states that come from every state you're in, and enqueue those ones and repeat until the whole thing is done. That was a little faster than I should have gone through it, but I want to get to this question, then I'll come back and go through it more slowly. Yes? The dictionary serves the purpose of keeping track of which state is the parent of each state. You also need a set to keep track of which nodes have been visited. They're calling it closed set. You can call it whatever you want. I think I called it visited in my implementation. So do as you please. If you're following this code, we'll call it closed set. But its purpose is to determine where you've been. And you need both. What happens if you don't keep track of where you've been? The frontier will expand exponentially because you'll always be able to go back to right where you were, and from there you'll be able to go where you were again. And so the branching factor is not contained, and therefore it just grows so fast, your computer will very quickly get overwhelmed. It turns out that simply keeping track of where you've been makes it more like a maze where there's always alleys to run down. Getting rid of that keep track of where you've been opens up the maze to infinite possibilities, and now your computer will never be able to handle it. You'll run out of memory before you find the goal with this problem. So let me say that in simpler terms. If your program takes a long time, the problem is your closed set of where you've been isn't working right. So go look at that, fix it, and then it will be fast. And if you do that, it must be fast. Why? There's only a limited number of states. And if you're not visiting one of them twice, well, you can exhaustively visit everything in a bad order eventually. And so it's not going to take forever if you're doing this set properly. So that almost certainly is your problem if your code is too slow. Excellent question. To answer that, I need to come back to the instructions. And I would like to point out there is an FAQ here. And these really are frequently asked questions. I've done this assignment a few times before, and these really will answer most of your questions. So do read these. And I've also given some code here, and I'll just let you in on a secret. Embedded within this code is pretty much all the hard stuff you need. So if you actually read and understand this code, this assignment's going to be super easy for you. I'd really rather you designed it all from scratch yourself and didn't use this stuff, but it's there for your benefit. So go ahead and use it, but do understand it if you do. How does one compare state objects in Java? Well, okay, let's talk about how we encode state. I know I'm going a little bit roundabout, but I will get to your question. So several people always point out, hey, look, these pieces have a shape. These pieces have a color. These pieces have a position. It's going to take a bit. How much information does it take to encode this whole board? So you need a class for a board and a class for a piece, and the class for a piece needs to know the color and the shape and its position. And where is the position? Is it the top left corner of the piece? Is it the bottom right corner of the piece? Turns out it doesn't matter at all, right? Because as long as you're consistent, it works. And if you pick top left corner, that works for this one. But what about this blue number 9? It doesn't have a top left corner. Is that a problem? It's actually not. Here's how I like to do it. Imagine that all these pieces are transparent overlays. You understand a transparent overlay, right? It just happens that they all have opaque portions, but really there's 11 pieces of transparency stacked up on top of each other. And they're all at position 0, 0. Can you see that? Well, now my start state is 22 zeros. 0, 0, 0, 0, 0, 0, 0, 0, 22 times. And now that perfectly describes the state of this board because I tell you where all the pieces are. Well, the corner of the transparent overlays is all in the top left corner. If you do that, it kind of makes it easy to implement this assignment. But you just have to think about the piece is not where it looks like it is. The piece is in the top left corner. And they're all in the top left corner. Now, how do you move a piece? Well, its transparent overlay slides around. So if this piece is at -1, 0, then piece number 10 will move to the left. And now its top left corner of its transparent overlay might be over here, but that's fine. And now the pieces just slide around until the red one gets to the top, and then you've solved it. when you report your answer, I'd like it to be in that form such that this is what the start state looks like. I'm arbitrarily calling this 22 zeros, and I want you to report the states through which you pass in the optimal solution from the start state to the goal state. And this is not the right answer. This is an example of how to report it.
Are those just in order of piece number?
Yeah. This is piece number 0, this is piece number 1, number 2, and so forth. And because this is 0, this is the red one you're trying to get to the top. So when this one reaches 0, 1, 2, 3, 4, 4, comma, negative 2, that's the goal. Horizontally 4 over and vertically negative 2. When you reach that state, you have reached the end of the puzzle. Okay, yeah.
Is it all right to look at it and say, okay, obviously, if it's going to reach the position 1 for the horizontal, vertical, if it's going to reach that point, it's going to be in the position of where the 10 is because the other positions. So are you allowed to just say that coordinate in particular, or should?
Yeah, you can say it any way you want. Basically, if your code finds the optimal solution, then how your code works is kind of, I don't care. But you do have to turn in the optimal solution, and breadth first search will find the optimal solution. And basically, you're not going to find a solution that's suboptimal in any easy way. So, well, that's not true. I had a student actually just do implement a random solver, just move pieces randomly. It ran for a darn long time, but it did find an answer, a suboptimal one. You could do that too, but, well, I won't accept it for this assignment, but you could do it for fun too. But do breadth first search, it'll find the optimal answer. Did I see a hand over there? Nope, okay. How do you know if a state is valid? Oh, the point I forgot to make is, okay, a lot of students will code up a class for the puzzle. It will contain an array of 11 pieces. Each piece will know its position and its color and its shape. And its shape will be a list of all the squares within it, and the squares will all have shape. What's bad about that solution that I'm talking about? Yeah, so remember, every time we fork the universe, we're kind of saying this state is going to be copied in this universe and in that universe. And we're going to have lots of copies of this. But the shape of the shapes of the pieces don't change, right? So, and how many copies of this board are you going to end up having in memory? Hundreds of thousands.
Static color?
Yeah, that's kind of the idea, is the color is static. It doesn't change. So now, in fact, color really is irrelevant because imagine this were black and white. It'd be hard for you to visualize, but the machine wouldn't know the difference. So color doesn't even exist in this problem. That's just there for your eyes only. Shape is a thing, but the shape doesn't change. So you definitely don't want that encoded in every single copy of your piece, or you'll have 100,000 copies all saying the same thing. The only thing a state really needs to represent are the things that change, which in this case are positions. There are 11 total pieces, which have X and a Y. So you can encode your entire state in an array of 22 integers. In fact, you can do it in an array of 22 chars if you want and save a lot of memory. In fact, I'm suggesting you do. Let's all encode state as new byte 22. This will make a nice, small, efficient, compact representation of state. And I happen to know any modern machine can easily handle 100,000 or however many copies we need to make of this type of encoding of state. People that code up everything they know about the puzzle in every single copy of every single instance overwhelm their machines, and Java can't handle it, and they come to me and say, this is an unsolvable problem, and they get very frustrated. And that's precisely why this is a great problem, is you kind of have to do it right for it to work at all.
You've got the big, and it's not...
There's this one that doesn't move if you want to do it that way.
The entire black square, including...
Yeah. If you call all the black ones a piece, because they could have a transparent overlay too, but they never move.
They never move.
So whether you consider that a piece or part of the problem, I don't care. Any way you want to implement it is fine. Yeah.
Why is the byte array size 22?
There are 11 pieces. I've numbered them 0 through 10.
Oh, okay. And then
They all have 2 coordinates, X and Y. And a char is enough, or a byte is enough to encode them all because only 0 through 9 and bytes can hold up to 255. If you really want to be efficient, you can do bit twiddling, and you really only need like 3 bits per piece. I think it's 4. Yeah. Well, no, because each piece has a width. Have to think about it. But you could make it really small, and it turns out that saving memory actually saves time with this. But don't waste your time. It works just fine with bytes. Okay? What is bit twiddling? That's when you use logical and an or to set and unset bits in integers or unsigned integers to represent what you want. So I would use that's called a nibble.
Yeah, there you go. So you could just,
Basically, the computer engineers love doing this type of stuff. The computer scientists just say, ew, memory's cheap these days. Just use it. But if you think of a number as looking like that, rather than whatever decimal we usually think of that, well, you could say these 3 bits are the encoding of the location of piece number 0, and these are the encoding of the location of piece number 1, and these are the encoding of piece number 2, and you could store your whole state in something like 2 integers. And people really do that kind of thing. I'm getting looks like that's crazy. I spent half of my childhood doing this. But that's back when I had 64K of RAM on my Atari 800XL, and I thought, that is so much memory, I'll never explore it all. And now nobody wastes their time exploring it all. Yeah, I used to just randomly peek and poke numbers into random bits of memory to see what my computer did. I wrote programs that would randomly pick a place of memory and just change the numbers in it, and I just sit there and watch it as my machine went crazy. And I learned so much by doing it. People just don't have the same experiences these days anymore. Because back then there wasn't a differentiation between user memory and kernel memory, so I was really changing what the operating system was doing randomly. And yeah, total security hazard by modern standards, but back then that's what you did.